The vast majority of engineered products have multiple components that need to fit together. Sometimes you need components to slip together easily, while other times you need components to press together and not come apart. There's a systematic way to design parts so that they fit together exactly the way you want on the first try every time, and in this video we're going to show you how. The engineering term for this consideration is fits and tolerances. Let's define these terms. Most of the time, especially in CAD, we just type a single exact number into the computer for our dimensions. That's called a nominal dimension. But when it comes time to actually make that part, we won't be able to manufacture the features to exactly those dimensions. Each feature might be slightly larger or slightly smaller than the number we originally typed into the computer. So we need to specify a tolerance, which tells the person manufacturing the part how much of a variation from our nominal dimension is acceptable.
Different manufacturing processes are capable of different tolerances. This chart shows a variety of different manufacturing processes, as well as a general idea of the tolerance that can be expected. It's important to remember that tolerance capability corresponds to a large production run, where factors like tool and machine wear, deflection, sharpening, and the natural variation of different processes apply. A very common mistake that new engineers make is selecting tolerances that are far tighter than necessary. As the tolerances become tighter, the cost to manufacture the part grows exponentially.
So how tight of a tolerance do you need? Tolerances typically come into play when designing fits. In some cases, you might want components to slip together easily, but not have a lot of perceptible play. In other cases, lots of relative movement is okay. You might even need to have two components come together permanently and not come apart. These different cases are called fits. Machinery's Handbook is the go-to reference for designing fits. Fits have a particular naming convention of a two-letter abbreviation followed by a number. The letters denote the type of fit, and the number corresponds to the tolerance class of the fit, with larger numbers representing looser tolerances. This graph shows all the standard ASME fits. The solid bars represent the acceptable tolerance of the shaft, while the hashed bars represent the acceptable tolerance of the hole. The scale of this graph corresponds to a 1-inch nominal shaft. This video deals primarily with ASME fits in the inch system, but there is a similar convention for metric. The naming convention is different, but the general concept is the same. For more information, you can reference Machinery's Handbook or ISO 286-2. Since the chart only applies for a 1-inch basic size, we need to use tables to design for other sizes. The process is easy, and we'll show you how with an example. The first fit we'll show you is the loosest. This is an LC11, and you can see there's lots of clearance. To design this fit, first we'll look up the LC11 column, then we'll find the row that corresponds to our basic size. At the intersection of the size and fit, we have a tolerance range for both the shaft and hole. Notice that these numbers are in thousandths of an inch. You'll use the same procedure to design all the other fits that we'll talk about.
These tolerances are extremely loose, so drilling the hole with a regular drill is sufficient. Hitting the shaft tolerance on the lathe is also no problem, and other processes like forming and extrusion will probably hit it as well.
This fit is used where you don't need accurate alignment of the mating features. The clearance around a bolt is a good example of this, since you typically don't use a bolt for precision alignment. This is a slightly tighter locational fit, LC9. It provides less clearance and has a tighter tolerance than LC11.
This is probably about the tightest hole tolerance that can be drilled, but turning shouldn't be a problem for the shaft tolerance.
You can see that the LC9 fit is a bit tighter than the LC11, but both can still be easily achieved with standard equipment and tooling. The next category of fits is called running fits. A running fit is typically used when you need two parts to mate together freely, or that's to say without any force, but you need some degree of precision in their alignment.
We ream this RC6 hole, but you can probably achieve this tolerance on a CNC mill if you compensate for tool diameter in the control. A drill is not likely to hit this tolerance every time. Depending on the size, this is probably about the tightest shaft tolerance that you can expect to hit consistently by turning.
This is the fit to use when you need two parts to align to each other, but some clearance is acceptable. This is the tightest fit that can be readily achieved with normal manufacturing processes and without undue effort. For the rest of the fits in this video, we're going to have to work a bit to hit the tolerances, and you're going to want to be absolutely sure you need this in your design, because you'll be paying for that care and attention. This is an Rc3 fit, which is a tighter running fit. In general, this fit is going to have almost no perceptible play.
This hole will need to be reamed or bored. You can also interpolate it on a CNC mill, but you will probably have to update the wear offsets throughout the production run to compensate for tool wear, and you'll need to be sure that tool deflection isn't causing the feature to taper with depth. A dialed-in and rigid lathe setup might be able to hit this shaft tolerance consistently, but as with the hole, you'll need to perform regular inspections throughout and adjust the wear offsets. A lot of parts, especially flexible ones or those made of tough materials, will require grinding.
Here's a comparison of the two running fits. The Rc6 has some perceptible play, while the Rc3 has almost none. Rc3 and tighter will precisely align components, but can still be assembled easily by hand. This next type of fit is called a transition fit, and it requires a slight amount of force to assemble and disassemble. However, there's absolutely no play once the pieces are assembled. The tolerance required for the Lt3 fit are about the same as the Rc3, but the range of the shaft has been shifted so that there is a slight amount of interference. If we add a bit more interference, we create what's called a force fit or a press fit. These fits usually require a press to assemble and are intended to be a permanent connection. We hope you enjoyed this video. If you have other topics in mechanical design engineering that you'd like to learn about, leave a comment and let us know. We're coming out with new videos soon, so please be sure to subscribe. Thanks!